The largest terrestrial planet in the solar system is the Earth, and the smallest ice giant, which is not terrestrial, is Neptune. Now, the diameter of Neptune is about 4 times greater than the Earth's, and inside the volume of Neptune fit 57 Earths. So the difference in size between the largest terrestrial planet and the smallest non-terrestrial planet in the solar system is quite large. But there are plenty of exoplanets out there that are between the size of Neptune and Earth, and there is a certain point in size, a line beyond which planets detected are pretty certainly not terrestrial. That blurry line is somewhere between the size of Earth and Neptune. So the reason that we can somewhat understand whether or not certain exoplanets are terrestrial is because we can know the density of exoplanets. Well, at least some exoplanets. And that is usually the exoplanets which are detected by 2 methods together. One method needs to give away the mass of the planet, like the wobble method, which gives away the mass of the planet by telling us how much it tugs, usually on its host star. And the other method needs to give away the size of the planet, like the transit method, which gives away the size of the planet due to dimming that it causes to its host star as it passes in front of it. So when a planet is detected through both of those methods, since density is just mass divided by volume, that gives away the density of the planet. Density of the planet tells us the likely composition of the planet, and that also tells us with some degree of certainty if a planet is terrestrial. That is because rocky terrestrial planets are much denser than non-rocky planets, simply because rocky planets are well made mostly out of heavy elements, certain rocks. So for example, the Earth is about 3.5 times denser than Neptune and about 7 times denser than Saturn. Saturn is actually even less dense than water. All rocky terrestrial planets in the solar system show that they are denser than all non-terrestrial planets. So anyways, study results show us already that usually as planets grow beyond 1.6 times that of the Earth, they also get lower in density, because they have enough mass to start capturing light gases, helium and hydrogen. So that means that planets that have a diameter beyond 20,000 kilometers also usually have a density way below the one for certainly rocky terrestrial planets. That is because they are either engulfed in gas, so they are not terrestrial, or maybe they are terrestrial, but they are mostly water ice, which is low in density. So the largest rocky terrestrial planets in the universe are about 20,000 kilometers in diameter. For example, Kepler-36b, a planet found in 2012. It is about 1,750 light-years away from the Earth, and it is orbiting a subgiant star. It is larger than the Sun. Now the estimates put the diameter of this planet at about 19,000 kilometers, so its surface area is 2 times greater than the Earth's. Its mass is 4.5 times that of the Earth, meaning its density is 6.8 grams per centimeter cubic, compared to 5.5 grams per centimeters cubic of Earth. This strongly indicates that this is a terrestrial planet. Also, the surface gravity of this planet is about 2 times greater than the Earth's, so you would be 2 times heavier there. Now, Kepler-36b is about 17 million kilometers away from its host subgiant star, so any hydrogen and helium is quite easily stripped away from its surface because of harsh solar winds, and also the extreme temperature at its surface makes it hard to keep the light hydrogen and helium with such a surface gravity. But if it had a slightly stronger surface gravity, then it would have started capturing hydrogen and helium. So about 20,000 kilometers is near the limit for rocky terrestrial planets. Beyond that, they start having too much gravity, which causes hydrogen and helium to be trapped on their surface. Now, the number of planets in the observable universe is about 46 stellion, since there is very approximately about a planet per star, and there are about 20 billion stars per galaxy, and there are about 2 trillion galaxies in the observable universe. considering that there are likely many planets out there in the universe that are roughly about 20,000 kilometers long, that have a surface gravity around 1.7 times that of the Earth, that have oceans of water on them. But since atmospheres of such large rocky planets would likely be much thicker due to a stronger surface gravity, that could allow for oceans of water that are on average 100 degrees Celsius hot. That is the boiling point here on Earth, at the sea level. But because their atmosphere would usually be thicker, that is not the boiling point on such planets. That is all because increased pressure increases the boiling point. Some speculations also say that the tectonic activity of 20,000 kilometer long rocky terrestrial planets would likely be usually much greater than that on the Earth. So continental movement on such planets would be happening much quicker compared to Earth. Still, what I talked about there is only rocky terrestrial planets. The size limit for water ice terrestrial planets is quite a bit above 20,000 kilometers. That is because water ice is much less dense than rock, so it takes more water in terms of size to get to the point at which the water ice planet starts having the necessary gravity to start capturing hydrogen and helium. So for example, the density of rocks on Earth's surface averages roughly around 3 grams per centimeter cubic, and the density of water ice is 1 gram per centimeter cubic. So 30 grams of water ice takes up a space of 30 centimeters cubic, while 30 grams of rock takes up a space of 10 centimeters cubic. Water is also the third most common molecule in the universe, since it's made out of very common elements. And many moons and planets in the solar system are either a 50-50 mix of water ice and rock, or are mostly water ice. For example, the moon of Saturn, Tethys, has nearly the exact same density as that of water ice, indicating that this 1,000 kilometer long moon is nearly just pure water ice. So considering that there are about 46 sextillion planets just in the observable universe, and considering that water ice is extremely common, there are quite likely many water ice worlds that have diameters up to about 28,000 kilometers. Now, the line in size beyond which water ice planets certainly start capturing hydrogen and helium is not as certain as with rocky planets, but a reasonable guess puts it at about 28,000 kilometers. Since very approximately beyond that size, the water ice planets generally start having enough mass to start having a surface gravity beyond the one for the Earth, so likely that makes them start capturing hydrogen and helium. So out of many sextillions of planets out there, there likely is a planet with a diameter of 28,000 kilometers that is nearly entirely water ice. And this is pretty much near the limit for terrestrial planets overall. Possibly it can get up to around 30,000 kilometers. So the water ice planet with a diameter of 28,000 kilometers has a mass about 4 times that of the Earth, and its density is about 2 grams per centimeters cubic. The compression effect of gravity and the likely central pressure and temperature makes the density that great, despite water itself being 1 gram per centimeter cubic. Now this water ice planet has a surface area 5 times greater than the Earth's. Its surface gravity is about 10% weaker than on the Earth, so it's quite similar. And because of that, likely these water ice planets near the terrestrial limit also in general have pretty thick atmospheres due to their gravity, and also the temperature ranges at which they likely exist would make it harder for the atmosphere to escape. So there we have our answers as to what the largest terrestrial planets in the universe are. So about 20,000 kilometers for rocky terrestrial planets, and for water ice planets, it's probably around 28,000 kilometers. Theoretically, there could also be pure carbon monoxide planets, for example. Carbon monoxide has a similar density to that of water ice, but it is frozen only at very cold temperatures of below around minus 210 degrees Celsius. So in the depths of some planetary system out there, where it is extremely cold, there could be pure carbon monoxide planets, Carbon monoxide is also made up of very common elements, oxygen being the third most common and carbon fourth. So it's comparably common to water, which is made up of hydrogen, which is the most common element, and oxygen, which is the third most common. Still, although massive carbon monoxide terrestrial planets are technically possible, it's not really certain that they do exist.